for the opportunity. It's great to see all of you.
Great. Now let's continue with the next invited speaker, which is Brad Knox. Are you there?
Hi, Miguel.
Hi, how are you? Thank you very much for participating.
Yeah, I'm glad to be here.
Are you able to share a screen?
Yeah, let me go ahead and try that out.
Okay. In the meanwhile, presenting the next invited speaker, Bradley Knox. He is the co-lead at the Bosch Learning Agent Lab. His research interests are centered around finding reinforcement learning solutions to autonomous driving and human-centered approaches to reward function design. So please welcome to Bradley Knox.
Thank you, Miguel. Can everybody see my screen okay?
Yeah, it is being shown.
Good, okay. All right, so as Miguel said, my name is Brad Knox, and I'm going to present on sanity checks for reward design. And this is work that I did at Bosch and in a group that's embedded inside the University of Texas at Austin Computer Science Department. And my collaborators on this work are Alessandra Allievi, Felix Schmidt, Holger Banzaf, and Peter Stone. Okay, so first let me present a little bit of motivation. I might be preaching to the choir here, but the big reason why reward design is important, at least in my opinion, is that an optimization algorithm like a reinforcement learning agent is going to be limited by the metric that it's optimizing against. So if we create a performance metric that doesn't really capture what the way we would evaluate behavior, then optimization might be effective with respect to that performance metric, or more specifically reward function, but still not achieve what we want it to achieve. And in this talk, what we're going to show is that reward design specifically for autonomous driving has consistently been problematic so far. And we're going to focus on autonomous driving as a running example. And this work is kind of meant for two audiences. One audience is an audience I think that all of you represent fairly well, which is people interested in alignment of reinforcement learning. And the other would be the autonomous driving community. So there will be a lot of autonomous driving in here, but think of it as a running example for general ideas that should apply across reinforcement learning. The problems that we're going to find in reward design, specifically for autonomous driving, we strongly suspect are represented well across applied reinforcement learning. That's both from talking to people and then also some survey data that we have but haven't published for another project. All right, so here's my brief outline. I'm going to finish talking about motivation and background. Then I'm going to briefly share some published reward functions for autonomous driving, just to kind of let you get the flavor for what some of these reward functions look like in practice. And then I'm going to present some sanity checks for evaluating any candidate reward function, whether for autonomous driving or elsewhere. And first, for background, again, I apologize if this part is painfully obvious and something that you know deeply. But this is very brief background on reward itself. Reward, let me see if I can get the laser pointer here. Okay, so let me know if you can't see my pointer. But reward is an evaluative signal that's given every time step to a reinforcement learning agent. And the reward comes through this reward function R that takes as input the state, the action, and the subsequent state. There are some simpler versions, but this is the most expressive version, barring stochastic reward. We are in this talk. I focus mostly on the return of a trajectory tau. So G is a function that uses a trajectory tau and evaluates it according to this, where at every time step, there's some reward value. For the purposes of this talk and simplicity, we're going to assume an episodic setting and therefore an undiscounted task. So we're not going to worry about discounting for this talk. The question of how to do reward design or how to evaluate a candidate reward function is not specific to reinforcement learning. There are a lot of other fields that have very similar concepts. So this idea of return for trajectory relates to the terms cost, fitness, utility, objective, if you add that you're trying to maximize or minimize it, performance and score, and then also the specific idea of reward is often called cost in motion planning control theory if you just flip the sign. So this is a big question that's applicable in a lot of different areas. I'm going to move on now to talk about a few published reward functions for autonomous driving. They're here left to right in basically an increasing complexity. And I'm only going to talk about the first two to kind of to give some hint of what these look like. So in this paper here by Isel et al., the reward function, the reward at each time step, is the unweighted sum of 3 attributes. One of them is this negative 0.01 for every time step. So you could think of that as a kind of a time penalty to encourage the car to get to the goal faster. Negative 10 if it has a collision, and 0 if there's no collision in that time step. And positive 1 if the agent successfully reaches a destination beyond an intersection. That's just their specific task, that there's an intersection you're trying to get through. So I'll just like note a few things about this. One, I think it's fairly understandable as these reward functions that are published go. It's quite understandable. The 3 components I think are fairly intuitively compelling. They all seem to be related to a core outcome that matters for autonomous driving, getting to the goal at all here at the bottom, getting to it while minimizing time, and avoiding collisions. Those all seem like important outcomes. Another thing, though, to note is in this work, I believe in almost all the work that we look at, time steps are 100 milliseconds. And so assuming that's right, then 10 seconds is 100. 10 seconds would be 100 time steps. 100 seconds would be 1,000 time steps. So that would be 1,000 times this, so negative 10. And so basically what this reward function is saying is if your policy can save 100 seconds, that's just as valuable in terms of reward, negative 10, as avoiding a collision. So already just thinking about this from reflection of like how important avoiding collisions is, it seems that there's a severe kind of unbalance in terms of how much collisions are being penalized, and that, you know, I would say saving 100 seconds on a drive is not equivalent to avoiding a collision. Okay, so moving on, here's another one. It gets a little more complicated here. It's also the unweighted sum. The reward at each time step is the unweighted sum of attributes, this time 4. There's one here that I won't go into details, but it's just encouraging going faster. So this also kind of has the time penalty feel, but it's a different way of doing it, encouraging going faster. It also has this reward, positive 5, for if the ego vehicle overtakes another vehicle. So this one to me is particularly interesting because passing another vehicle, I believe, and I don't think this would be controversial, but passing another vehicle is not one of the outcomes that matter for autonomous driving. It's more of a means to an end. So this seems to be an example of what's commonly called reward shaping, where they're hinting at what behavior should be done to drive well, but using the reward function to do that hinting. Another form of hinting here is in the next one, where there's a penalty if the ego vehicle changes lane. So presumably this is related to safety or maybe passenger comfort. But also this seems to be something that's more of a means rather than an end. Changing lanes in and of itself is not an outcome that matters one way or the other for autonomous driving. I won't go into these other two, but you can see there's some increasing complexity. There starts to be weights that vary in more terms. And in this one, there's terminal reward that's defined. And then for transitions that don't terminate the episode, there's a different reward function. All right, so that's just kind of some examples to get you acquainted. Okay, and so now I'm going to move on to the core of the talk, which is sanity checks for evaluating reward design. And they'll specifically be applied to autonomous driving. And what we did for this was we reviewed 19 papers published, I think, between 2017 and 2020. And they're all in autonomous driving, involve reinforcement learning, and contain a reward function that they optimized against. And they're generally at top conferences like RSS and ICRA, AAAI, things like that. They're all either from top conferences, good journals, and a few of them are from autonomous driving specific venues. And 10 of these we exhaustively characterized. So some of the analyses I'm going to talk about required filling in basically every last detail, typically by emailing the authors to get information that was not in the paper. Okay, so we have 8 sanity checks, and in these slides, sometimes they're called tools. So consider that interchangeable. And I'm going to talk in detail about, I believe, 4 of them. And the first one is to identify unsafe reward shaping. So this term, if you're not familiar, is adding reward. So in addition to the true or environmental reward that really aligns to your performance metric, reward shaping is providing further reward to aid learning. And the most common way to do this would be to provide behavioral hints or heuristics, like we saw in that reward function that gave some additional reward for passing cars. So first, I want to kind of look at what some authorities in AI and reinforcement learning say about designing performance metrics and specifically reward functions and relating that to reward shaping. So in Russell and Norvig, they say, as a general rule, it is better to design performance metrics according to what one actually wants to be achieved in the environment, rather than according to how one thinks the agent should behave. Sun and Bardo, in their textbook on reinforcement learning, agree in almost the exact same phrasing. And then they add that imparting knowledge about effective behavior is better done via the initial policy or initial value function. All of this is open to debate, despite their authority for having written standard text in AI and reinforcement learning. But I think that kind of sets some initial thoughts on how you would design a performance metric, and a reward function is a type of performance metric. So my shortened version of these is to specify how to measure outcomes, not how to achieve them. And if you take these on face value, they seem to be saying not to shape rewards. However, there is a body of research on safe reward shaping. And I just want to be clear here that safety is not about collisions. What I mean in this field, what safety tends to mean is that the reward shaping has certain guarantees not to harm learning. So perhaps there's a true reward function and a set of optimal policies with respect to that true reward function. And then when you add reward through shaping, reward shaping, maybe you can guarantee under a certain technique that the set of optimal policies hasn't changed. So there's a handful of techniques that have these guarantees with some assumptions that I think are often under noticed. But in the desirability of these techniques is still controversial. So there is some safe reward shaping, and I think it's very defensible to do it. I want to add, though, an assertion here, or kind of a proposal of a way of evaluating reward shaping. And that's that if no effort is made to establish that an instance of reward shaping is safe, then we should consider it unsafe. Using driving as an example, if a car company makes a car and does no crash testing at all, and then sells it to the public, yes, there's no test saying that it's unsafe, but the lack of testing itself is a form of being unsafe. So I think that's a decent analogy to this, that reward shaping is unsafe if you don't try to establish that it's safe. All right, so applying this idea of just identifying unsafe reward shaping to these reward functions that were published for autonomous driving, 13 of the 19 papers do have reward shaping. Here's some examples of behavior. So these are components of the reward function that encourage certain behavior. So staying close to the center of the lane, passing other vehicles, not changing lanes, increasing distances from other vehicles, which is kind of safety related, avoiding overlap with the opposite direction lane, and minimizing steering angles. I'm happy in the time of questions to debate any of these. We're fairly confident that we could call these behavioral hints and not core outcomes, but I think it's fine for someone to disagree. So if you remember, I talked about 10 papers that we exhaustively characterized. 8 of those had reward shaping, and of those 8, none of them explicitly describe a separation of their shaping rewards and their true rewards. So they only had one reward function, and it had these behavioral hints in it. So we don't actually even know what the true performance metric is, at least in the form of a reward function. None of them as well use a recognized method of safe reward shaping or discuss the safety of reward shaping. There's also some other issues which I won't get into for time. And so that concludes the first tool, which is looking for looking for reward shaping and then asking, is it safe or not? And the reward functions that we looked at don't do well according to this metric. 8 out of 10, 13 of 19 use reward shaping, and then for the 8 that we looked at more closely that use reward shaping, none of them did these other 2 things that are important. All right, so now on to the second sanity check. So this is a really simple one, actually. And all you do is you find 2 trajectories where human stakeholders would all agree that one is better than the other. And what we're going to do is our 2 trajectories are going to be tau crash, where the car goes halfway to the destination and then crashes, and then tau idle, where the car safely just doesn't move. So this is kind of like, if you wanted to go somewhere and you decided it was too dangerous to go, or you just didn't go, period, whatever your motivation is. And so I hope everybody would agree that not driving is better than driving and having a collision with certainty. So the question here is, we have this ordering that tau idle is preferred to tau crash. Now, if we evaluate these trajectories with a reward function, the question is, will that specific reward function also prefer tau idle over tau crash? And to do that evaluation, these are abstract trajectories. There's not like a core state in action sequence, and it wouldn't even hold across all these different papers because they have different settings. But in the appendix of the related paper, we list out our assumptions to make actual calculations of return. And what we find is, of the 9 exhaustively characterized papers, reward functions that allow us to do this analysis, 7 of them actually prefer the certain crash over not driving. So that's a big and a big result from a fairly easy sanity check to implement. So now we're going to go to a more sophisticated sanity check that builds on the last one. And that's to compare what are sometimes called indifference points. And I'll explain that in a moment. So now we're going to add a third trajectory, and that's just a successful one, tau destination, tau dest. And the agent, there are going to be two options here. So two kind of high level actions. And we're going to ask the reward function which one's better with respect to return. So actually with respect to expected return. So option A is just the safe idle one, not moving. Option B is a lottery or probability distribution over tau crash and tau destination, where P is the probability of having tau crash. And so this actually, I think, is very representative of what we often have to do when we're thinking about driving somewhere. So say there is a storm outside, and you're trying to decide, is it safe enough to drive right now, or should I wait for different conditions? And in a sense, you're trying to decide what's more valuable, what's the higher return, not driving or driving with some risk of crash and some probability of getting to your destination. All right, so here's the math behind it, or at least some of the math behind it. We're able to find an indifference point, which is the P, such that these two options, neither is better from the reward function's perspective. So as you scale that probability of crash versus success, then there should be a point where the agent, because tau idle is the middle in the preference ordering, there should be a point where a probability at which the agent is indifferent between option A and option B. And specifically, once you evaluate the return for each of these abstract trajectories, ground them out with assumptions to actually get numbers for the return, then you can solve for that indifference point P by this simple equation here. So once we have P, the indifference point for a specific reward function, we convert it. I'm going to be hand wavy here just for time. We convert it to a proportion of successful drives to colliding drives, and from that, we, along with a known or estimated distance of a successful drive, we can calculate the kilometers per collision at the indifference point. So this is a kilometers per collision, at which if the agent does better than that, the reward function would say drive, and if it's worse than that, the reward function would say don't drive. So here, excuse me, here are the results. On the left are the 7 reward functions that already failed the second sanity check. So their indifference points don't actually exist. I think if you try to do the calculation, you'd end up with a negative number. A negative probability would be meaningless. And so here are the remaining 2. And then on the right, we have actual people. So here are the two groups of the safest age group and the least safe age group of US drivers. And importantly, it's worth pointing out that the 16 to 17-year-old US drivers are deemed permissible by society. So despite them having higher risk than the older drivers, that risk is considered permissible by society. And they might not be looking at these exact numbers to make that determination, but it's considered permissible. And then here's our estimate of drunk teenagers, and drinking and driving is considered impermissible. So these are kind of lower and upper bounds, in a very rough sense, of societal norms for where the indifference point should be. And we see that the most risk-averse reward function would allow driving at 1,000 times the rate of the drunk US teenagers. So there's really a mismatch here in terms of what we want safety-wise in the reward functions that are being published. I'm actually going to skip this for time since I'm running a bit long. And lastly, of these sanity checks, I want to mention that of the 8 papers whose authors shared their reward design process over email with us, every single one of them used trial and error reward design, which I think is a somewhat common term, but the big issue here, in my view, is that this is a very common technique of, you've got a candidate reward function, test an RL agent on it, observe that, and then change the reward function and repeat. There's a common practice, and yet nobody studied the effects of it. And basically the human designer, the reward designer, is acting as an optimization algorithm. We know there can be various issues with optimizing in a specific setting and possibly overfitting to, to other setting, or with respect to other settings. But nobody's looked at this. So this is a very untested and not condoned by any, definitely not in Sutton and Bardo or any paper I'm aware of, period, that really condones this in a rigorous way. So this really needs to be looked at more carefully, which actually we have a project that's focused on that right now. So here's the 8 sanity checks, just to review the ones I talked about. Identify unsafe reward shaping, compare preference orderings over trajectories, compare indifference points, and identify trial and error reward design. And I want to mention, as kind of to close out, some caveats and extensions of the work. So these are just sanity checks. Basically, they're ways of identifying flaws or potential flaws in a candidate reward function. And to my understanding, there's no methodology out there for comprehensively evaluating whether a reward function is aligned with a set of human stakeholders. This is a deeply difficult problem that needs expertise on the RL side, but also on the human side. And I think it really direly needs to be done. And I think there's some related work in other fields that could be pulled from. Also, just a caveat, the whole time I've been talking about reward functions for autonomous driving overall, but often these reward functions or cost functions are for lower level modules that are not doing the entire decision problem of autonomous driving. Instead, they might be executing command like a path planner that's executing a command to do a lane change to the right. So the reward function for these lower level modules might, is almost certainly actually different than at the highest level, since they have an extra command that's been given to them. And to my understanding, this kind of hierarchical reward relationship also has not really been looked at. So some of the papers that we look at and that don't do well in terms of our sanity checks might be seen more generously in view of that some of the RL algorithms are not doing the entire problem. Some of them are, but some of them are focused on lower level modules. And then lastly, learning from correctly scaled reward, where collisions are given an immensely negative reward, presents several challenges from the gradient size, from updates, but also just you could have a early agent that has a bad policy, as early agents do typically, and it might correctly learn that it shouldn't drive because the penalty for driving or for having a collision is too high, but then it won't learn. So there's some interesting questions about how do we actually use reward function that could pass these sanity checks, but also allow for learning effectively. So just to close, there's a website for this paper. It's my name, bradknox.net/reward-misdesign. The actual paper title is Reward Misdesign for Autonomous Driving. And lastly, I just want to close with a quick pitch. I actually am leaving Bosch and joining Google Research in about 10 days or so for a specific project that lured me away from what's been an amazing job. And it creates a opening for someone to take my place there as the scientific site lead. And just to review, at Bosch has this site inside the computer science department. We have offices in the computer science department at UT Austin. We collaborate with Peter Stone and Scott Neekum there and others. And we're hiring a research engineer and a scientific site lead. And it's a wonderful, wonderful position. And the group is going to grow. So it's also like an opportunity to get a leadership position early on. So if you're interested, you can find my email address on my website, bradknox.net. Feel free to reach out to me for more information. With that, I'll stop and take questions if there's any time remaining.
Thank you very much for your presentation, and congratulations for the moving up. We have one question on the chat. There, Domen asks about, he's curious about your views on whether a simple reward function is enough for tasks like autonomous driving, or do we need approaches like transfer learning or multitask learning for complex tasks, such as, for example, driving in the US versus driving in Europe could possibly benefit from transfer learning?
Yeah, I actually think that what reward shaping, I think to a large extent, or maybe even fully, the consequences of reward shaping are, they're dealing with an exploration problem. They're pushing the agent to try certain things that maybe it wouldn't try very often otherwise. So to be able to use, quote, correct reward, or at least reward functions that pass these sanity checks, it would, not to do reward shaping potentially, I think other techniques are needed, and transfer learning, I think, is one of many really potentially effective techniques. Other ones would be using human data, whether demonstrations or otherwise, to improve the learning speed, using some more recent exploration techniques that are better than we traditionally use in reinforcement learning. I think there's a lot of possible approaches. But yeah, I think the short answer is yes. I think transfer learning is an incredibly important area, and I think it actually is probably needed to reduce the amount that we rely on reward shaping.
Okay, great. Thank you very much again, and for participating and presenting this interesting talk.